Welcome to this video in the Atomic Theory chapter. This is 3.5, Atoms and Electrons Continued. In today's video, we're going to be delving deeper into electrons, and our topics are going to include a very critical and important sublevel and orbital summary. We're going to teach you how to write SPDF orbital notation. We're going to present to you guys the rules of filling, namely the Aufbau principle, the Hund rule, and the Pauli exclusion principle. And then we are going to show you two exceptions, and believe me, there's more, to the rules of filling. So if you haven't already done so, please make sure you have your chemistry notebook handy. You got a pencil and your periodic table at the ready, and you will also need your plan sheet to practice what you've learned. So without any further ado, let's get cooking. I want to lead off this video with some information about the atom and atomic structure that is absolutely critical, and you have to know. It is essentially a numbers game. What you need to understand is that how many orbitals you have, so we're talking about the number of probability areas where you'd find electrons, will determine the class of sublevel. So what we see here is a chart. This chart is important and needs to get copied down. And so the way it works is that if you have one area of probability, it is considered an S sublevel. If you have three areas of probability, three orbitals, it is considered a P sublevel. 5 area of probability are considered a D sublevel, and 7 is considered an F sublevel. Another important fact that you need to make sure that you understand is that each orbital that we see here can hold up to 2 electrons. Now, what does that mean? Well, in your S sublevel, an S sublevel is one orbital, and in that one orbital, it can hold 2 electrons. So your S sublevel can hold 2 electrons max. That is different than your P sublevel, which contains 3 orbitals. Well, in every orbital, you can hold 2 electrons. So the reality is 3 orbitals times 2 electrons. In a P sublevel, you can hold 6 electrons maximum. In your D sublevel, because there are 5 areas of probability, 5 orbitals, you can hold a total of 5 times 2 electrons to get you 10 electrons max. And obviously, in your F sublevel, which is 7 orbitals, you can hold a total of 14 electrons. So that's important for you to commit to memory, as is most of this chart. So do yourself a favor, pause the video now, and make sure you commit this chart to your notes, and then memorize it. Piggybacking on how many orbitals are in each sublevel, what I want to focus on now is how many electrons can be held in a principal energy level or a shell or a ring. The way it works is pretty simple, and you guys will have to memorize this too. Your first shell can hold 2 electrons, the second 8, the third 18, and the fourth 32. Why that is directly corresponds to how many sublevels and directly orbitals each principal energy level or shell will have. Harken back to the slide that we just did. In the first principal energy level, we know we only have an S sublevel. S sublevels are one orbital and they can only hold 2 electrons. In the second principal energy level, well, we can hold a max of 8 electrons. Why that is because we have an S and a P sublevel. So remember, in your S, you can hold 2 electrons, and in your P, you can hold 6 electrons. In the third, we can hold a max of 18 electrons because we have an S and a P and a D sublevel that are there. Remember, your D sublevel can hold 10 electrons. So we have 2 plus 6 is 8 plus 10 is 18. And your fourth has the S and the P and the D and the F sublevel, and the F can hold 14 electrons max. There are 7 orbitals that are there, and what you guys have to do is know up to the 4th principal energy level. There is an easy trick to remember this, and that trick is 2n squared. The calculation of 2n squared, where n is equal to the number of the principal energy level, can help you figure out the maximum number of electrons that you can hold in any ring shell principal energy level. The way it works is like this. Let's say we have a question where they ask you how many electrons can the 4th principal energy level hold? Well, in a case like this, we do a simple calculation. If n is now going to be equal to 4, we would say 2n squared. 2 times 4 squared. In the order of operations, we are going to do our exponent first. 4 squared equals 16 electrons, and we're going to now multiply that by the 2 that's there, and that tells me we have 32 electrons total. With that, it is time to move on to the rules of filling, orbital notation, and electron exceptions. So in terms of electrons and orbitals, there is a simple fact that electrons and energy levels will fill in an orderly and predictable fashion. How do they fill? Well, there are 3 rules to memorize that will govern the way that your orbitals will fill with electrons. And if you were in class, it is very much like the Higgs activity that we did. Our first rule number 1, is known as the Aufbau principle, and you may remember that from an earlier video where we mentioned it. Aufbau means build up in German. What are we building up? Well, electrons, of course. The way the Aufbau principle works is that available electrons fill the sublevels and orbitals in the lowest energy levels first, then proceed on to the higher ones. Remember, energy is determined by distance from the nucleus, so your lowest energy levels are here while your highest energy levels are there. You will notice that some of the sublevels of the 4th principal energy level are lower energy than some of the sublevels of the 3rd principal energy level, and that's what makes the order of filling so crazy. The Aufbau example that everyone always goes to is why 4s will fill before 3d when 4s is part of a higher principal energy level. Our next rule is known as the Pauli exclusion principle. Pauli exclusion principle says every orbital can hold a maximum of 2 electrons. Well, wait a second. You know that because we just talked about that. But what you don't know is that the electrons in the orbitals can be graphically represented by arrows. And the arrows are these guys that we're seeing here. This is 1 orbital. This is 3 orbitals. So this would be an example of an S sublevel. This would be a P sublevel with the 3 orbitals. And you will notice that each arrow represents an electron, and that if they are occupying the same orbital, they were spinning in different directions. The last rule that we have to get to in the rules of filling is known as the Hund rule. The Hund rule basically says that all orbitals of a sublevel must be occupied before any electrons can double up. Now, what does that mean? Well, let's take this example here, which is carbon and has 6 electrons we have to fill. Since we understand that the Aufbau principle says we're going to fill the lower energy levels before any that are higher, we're going to go from 1s all the way up to 2p. The Pauli exclusion principle says we are going to spin them opposite one another, but now the Hund rule says we got to sequentially fill the orbitals, and we can't double up before we have single occupancy. So let's take these 6 electrons. In the first energy level, I would put 1 up and 1 down. Moving on to the second, 1 up and 1 down. And now when I get to the 2p, this is where things get crazy. I have 2 electrons to place. The correct orientation of these electrons is 1 here and 1 here, not 2 that are there, because that doesn't follow the Hund rule. The Hund rule says you cannot double up until each orbital that is in the sublevel has already been occupied by at least 1 electron. So what is this all good for? Well, we use this to write orbital notations. So let's get into orbital notations on the next slide. Orbital notation should look pretty familiar to you once we actually see an example of it, because it's essentially your Higgs activity that we did. What orbital notation really is a special way of writing electron configurations that will provide us more specific information about the electrons in an atom of some element. What orbital notation is going to show us is each orbital that is in a sublevel and the electrons within that sublevel and specific orbitals and how they spin. Here's an example. Let's say I wanted to write orbital notation for the element phosphorus. Well, I have to begin by writing my regular SPDF electron configuration, which I see here. And phosphorus is the 15th element. There are 15 electrons. So the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. So with that said, the orbital notation is going to look like this. I am going to take each principal energy level, and I am going to separate within each principal energy level I'm going to separate the sublevels and draw each individual orbital. So here I see the 1s sublevel, and I see the 1 orbital that's within it. The 2s sublevel and the 1 orbital that's within it. The 2p sublevel, 3 orbitals. The 3s, 1 orbital. The 3p, 3 orbitals. So you can see here what I have essentially done is I have used these lines here to represent the orbitals within the sublevel. Now what we have to do with this is we want to represent the electrons. The electrons are represented by arrows, and how they spin is represented by directionality of the arrows, as we saw in our last slide talking about the Pauli exclusion principle. So now I go to my electron configuration. I see, all right, in my first principal energy level, I have an S sublevel, I have 2 electrons. I'm going to represent them by 1 going up, 1 going down. So now in my 2s, I have 2 electrons. I'm going to put 1 up, 1 down. In my 2p, I have 6 electrons, and here's where the rule of filling comes in really handy. I'm going to put 1 here, and 1 here, and now I'm going to double up for my 6 electrons. Now I go to my 3s, there's 2 electrons. I'm going to go 1 up and 1 down. And in my 3p, which is my outermost sublevel, I have 3 electrons. I'm going to put 1 here, 1 there, and there. So what we see is in our valence shell, which is the 3s plus the 3p, I've got 5 electrons, and I am now seeing the orientation they take and their spin and their distribution. Stop the video now and write down the summary of how to write orbital notation. Unpause the video when you're ready to move on. Let's now try and apply what we did in the summary on the previous slide and do some guided examples of orbital notation. Let's say I want you to write the orbital notation for boron. Well, the first thing we have to do is write an SPDF electron configuration. And what's nice is I've given that to you. I figure you got that skill in your pocket already. So what I have to do now is I have to represent each sublevel and the orbitals within. I'm going to do so by drawing them with lines. I know in a 1s sublevel, I know that there is 1 orbital. So I'm going to draw 1 line there. And I'm going to write 1s on it like that. I know in a 2s sublevel, there is also 1 orbital. So I'm going to draw 1 line to represent that 1 orbital. And I'm going to write 2s. And now I'm going to draw my 2p sublevel, which is 3 orbitals, 1, 2, 3. And I have the skeleton and the makings of an orbital notation. So what I got to do now is distribute these electrons. In the first sublevel, there's 2 electrons. I'm going to put 1 up and 1 down. In the second, there's 2 electrons. I'm going to put 1 up and 1 down. And in the third, I'm going to put just that 1 lone electron here. And what I have is now complete. That is boron's orbital notation. Fluorines will get a little more difficult. We have the same distribution of orbitals and sublevels. So I'm just going to draw them in here and write 1s, 2s, and 2p. And now what we got to do is we have to distribute the electrons. I'll just do it in a different color just for giggles. So in my first sublevel, I have 1 orbital, I have 2 electrons, 1 up, 1 down. In my second, I have an S sublevel, 1 orbital, 2 electrons, 1 up, 1 down. And now here is where the rules of filling will come in pretty handy. I've got 5 electrons that I want to go fill, 3 orbitals. So I put 1 in the first. I'm not going to double up here because I have to have 1 in each orbital of the sublevel before I double up. I'm going to put 1 there and 1 there. That's exhausted 3. That leaves me 2. So now I can double up. And here is the orbital notation for fluorine. One of the unique things that you may actually see is the orbital notations that get written in ways other than the lines that are here. Sometimes you can see the orbitals distributed in boxes, or sometimes you can see them, sometimes you can see them in circles to represent the orbitals. So it doesn't really matter how you're going to see it. You may see it anyway. Be prepared. I really don't care how you write it. The one way my teacher did it was with lines. And of course, I'm all about tradition. So I'm going to teach you that as well. So now it is your turn. Here are 3 atoms I wish for you to write the orbital notations for. You're going to have to start by writing the SPDF electron configurations, but pause the video now and then unpause when you think you are ready for an answer. All right, if you did this correctly, here are your orbital notations for these 3 atoms. Remember, if you did get anything wrong, please go back into the video and figure out what you did, or you can certainly bring the question that you may have to our next session. Now it is time to talk about probably the most important thing in this video, and it is the exceptions to your electron configurations, things that do not follow the rules of filling. Of course, it's like in a language class, it's like having irregular verbs. Well, this is one of the irregular verbs in our chemistry class. So let's check this out. So I'm going to start off our last segment of this video with a little interactive piece. I want you guys to write the SPDF electron configuration and the orbital notation for both chlorine and chromium. So pause the video now and then do that. Unpause when you think you've got the answer. All right, if you did this correctly, here's what you should have gotten for chlorine. It should have been 1s2, 2s2, 2p6, 3s2, 3p5. And we have an orbital notation that looks like this, where our s sublevels all have one orbital, our p sublevels have three. Everything is filled with the exception of this last orbital in the 3p sublevel, which only has one electron. Now, on to chromium. If you did chromium according to all the rules of filling that we learned previously in this video, we should have gotten this electron configuration here, and it should have ended with 3d4. But now, the bad news. If you ended your chromium electron configuration with 3d4, that is the wrong electron configuration. So let's talk about why this is wrong. If we look at the box from the periodic table that came from New York State, you will notice a couple different things. First thing you should notice is there are 13 electrons in the third principal energy level. So let's go count them up. Here I have 2 electrons, here I have 6 electrons, and here I have 4. 2 plus 6 plus 4 gets me a grand total of 12 electrons and not 13 like New York said. And my fourth principal energy level, my valence shell, only has 1. Yet here, if I look at my highest principal quantum number in sublevel, which is a 4 here, it tells me there are 2 electrons. So what gives? Did New York State indeed make errors in the periodic tables that they distributed to everyone? Or is it something we did? Well, it turns out that even if you wrote 4s2 3d4, you probably did everything right according to the rules, but the reality is that is not what is the real chromium electron configuration. So let me tell you a story about atoms. Atoms want to have the lowest energy state possible. They want to be as close to what we call the ground state as they can be. And there are some configurations of the electrons that lend themselves to lower energy states than others. This electron configuration here, where we see we have 4s2 3d4, is a slightly higher energy state than really what it turns out to be in real life. So let me show you how we get from this to this that we see here. Ultimately, what happens is you notice there is 1 valence electron according to New York State. We have 2 valence electrons here. That is because in the 4s sublevel, in order to attain a lower energy state, chromium will take this 1 valence electron there and will promote it. And it's going to promote it into the 3d sublevel. So that actually gives us 4s1 3d5. Here's a cleaned up version of that. And what that does is by promoting the electrons, it increases stability. So the reality of what we get is 4s1 3d5, and now that jives with what New York State was sort of telling us. The important takeaway is the following. Completely filled sublevels are the lowest energy state and most stable possible. That is what we see here with our 1s, 2s, 2p, all the way through 3p here. And what happens then, if you can't have a completely filled sublevel, the next most stable configuration is a half-filled sublevel. In this case, by making this a 4s1, we are half-filling this. And now we are promoting the electron to 3d, which used to be 3d4, but now it is 3d5, which is another half-filled sublevel. So half-filled sublevels are the next best thing if you can't have completely filled. And the door prize goes to the partially filled sublevels. They are the least stable and the highest energy state that there is. So the important takeaway is to know that chromium will violate the rules of filling to reduce its energy and increase stability. Our next example of an exceptional electron configuration is copper. And if you drew out copper's SPDF electron configuration according to the rules of filling, we would end with 4s2 3d9. But when we peek at what New York State gave us, we notice there's only one valence electron. So here we have 2. They told us we have 1. If we look at the orbital notation, we can see why New York State is once again correct. In this orbital notation, I see that I can achieve a greater stability and lower energy state by taking that electron out of the 4s and sticking it into the 3d that is there. Again, it's the same rationale that completely filled sublevels are the most stable and lowest energy state. Half filled is next, and the door prize for that would be the partially filled sublevel. So once again, we have a promotion of an electron to achieve greater stability. You're going to see, guys, that this is something which shows up throughout the periodic table, particularly in the larger elements where the sublevels overlap. Here's a picture. You guys can see here that once you get deep into the innards of that periodic table and we start to introduce the F sublevel and a lot of the higher D sublevels, all these energy levels overlap and they virtually sit on one another. So it is very easy to move electrons from one sublevel or orbital to another in order to achieve stability. So that's pretty much it for me. We covered a whole lot today. Make sure if you have any questions on anything, whether it was on the rules of filling or orbital notation or the exceptions to electron configurations, you bring those queries to the Burning Questions segment tomorrow. It has been my pleasure to teach you more about electrons. I will see you again on the flip side. Peace out.
That's all, folks.